Good morning. Today I will be discussing about MR PET instrumentation. Mutual interference between MR and PET. Positron emission tomography imaging allows the observation of metabolic and physiological processes of organs in their normal and diseased states. However, its ability to show anatomical details is limited. Therefore, the complementary use of PET with computed tomography or magnetic resonance imaging is becoming common practice and has largely been facilitated by the development of the dedicated programs which enable the combined display and analysis of images from both modalities. The advantages of combined analysis have led to the development of subsequentially combined PET-CT scanner and to the abandonment of PET-only scanners. When compared to CT, MR, when compared to CT, MRI also offers a large number of contrast mechanisms for functional and physiological imaging, thus allowing for single exams delivering metabolic, functional, and structural data when using hybrid PET MR devices. Moreover, the realization of truly simultaneous acquisition is more difficult to achieve in the case of PET and CT, since both modalities use high energy photons as the information carrier and both modalities also use scintillation detectors for detecting them. Furthermore, although it is possible to discriminate the photons by their energy, CT requires a photon flux which is several orders of magnitude higher than that for PET imaging, and which will saturate the PET detectors, making it insensitive to inhalation radiation. In contrast, MRI uses radio frequency RF for excitation and for detection of signal from the nuclei. This can be more easily combined and mutual interference can be better minimized. Nevertheless, the strong static magnetic field, the switched magnetic gradient fields, the use of high power RF transmission, and the extraordinary high sensitivity of MR for the detection of RF signals require very careful design when combining MR with PET in a simultaneous device. One major problem in the development of a signal integrated MR PET device is the strong B0 magnetic field, which not only impedes the use of classical photomultiplier tube for photo detections but also prohibits the use of many essential electronic components from being arranged close to the imaging FOV of the MR system. The reason for this are manifold. The B0 magnetic field may lead to displacement of loose components. Some components become ineffective, for example, ferrites, which are used in many electronic devices, have a saturation flux density of approximately equal to zero point 0.3 Tesla, and many plugs, integrated circuits, sockets, and pins of electronic components contains ferromagnetic materials. MRI not only requires a strong magnetic field, but it must also be extremely homogeneous with the deviation of only a few parts per million ppm over the whole MRI FOV. MRI images already become significantly distorted by field variations of approximately change in delta B0 approximately zero point 0.1 ppm into B0 magnetic field. Thus, the image distortion effect thus the image distortion effect that a magnetic component of volume Vd causes at a distance r can be estimated by evaluating its magnetic dipole strength according to the equation Hd is equal to Br divided by mu, into md divided by 2 pi rho d r cube, where Br is the saturation remanence of the material, sigma rho d is its density, mu is the permeability, and md is the total mass corresponding to the volume. For instance, a volume of 0.1 mm cube ferrite causes a field variations of approximately 0.1 ppm in a 3 Tesla scanner at 2.5 centimeter distance. However, paramagnetic and diamagnetic materials can also affect the MR images. Therefore, potentially all materials required for the construction of the PET systems inside the magnet bore can lead to MR image distortion degradation. This can be especially relevant for gamma shielding materials, which are often used in PET imaging devices to protect the scintillation detectors from inhalation radiation emitted outside the PET FOV, and also for the scintillation crystals, which are key component for PET and have a considerable volume in order to stop the gamma photons. To overcome this problem, it is preferable to use materials with only a small susceptibility mismatch compared to the surrounding medium. To meet MR compatibility criteria while designing a PET device, only materials with a high susceptibility mismatch smaller than 10 ppm compared to water are recommended for use. The volume magnetic susceptibility of water at 37 degrees Celsius is 9.5 into 10 to the power minus 6, sorry, minus 9.05 into 10 to the power minus 6, and for human tissue it ranges from minus 11.0 into 10 to the power minus 6 to minus 7.0 into 10 to the power minus 6. The susceptibility for selected shielding materials, scintillation crystals, and other materials used in PET devices are summarized in table 1.10.1. While many typical material fulfill the condition mentioned above, some of them still cannot be used for building a combined MR-PET devices. For example, a common GSO scintillator and nickel, which is often used in a small amount in connectors and pins of electronic components. In addition to magnetic compatibility, there are further limitations on the materials that can be used. Table 10.1 suggests that lead, which is which is inexpensive and efficient shield, could be used in hybrid MRPET devices. However, lead is a good conductor, and when exposed to the switching gradient fields, ED currents will be induced on the surface of the lead. The ED for materials with homogeneous magnetization, M is equal to uh, chi divided by mu into B, and a thickness d of the conductive material considerable thinner than the corresponding skin depth and frequency f, the electromagnetic radiation, the power dissipations due to ED current can be approximated by equation P is equal to pi square capital M square dq f square capital A divided by 6 sigma m, where sigma is the density of the material, uh, where rho is the density of the material, sigma is its resistivity, and A is the surface area. For material with homogeneous magnetization MB and a thickness D of the conductive material. Oh, sorry. The power dissipations due to ED current can be approximated by equation 10.2. This power dissipation can lead not only to the heating of the gamma shields, but also appears in other large conductive structures like copper planes, easy power supply, and ground layers of printed circuit boards (PCB) in the PET data acquisition electronics. In addition to heating effects and large induced voltage, a second important eddy current related issues which may lead to failure of electronic components is the creation of eddy current induced counterfields that are opposed to its cause, Lenz's law. These are especially relevant for the gradient system of the MRI systems, since eddy current fields can be sufficiently strong to distort the applied gradient fields. As the gradient fields are used for a spatial encoding of the MR received signals, their distortions lead to image distortions and potentially other MR image artifacts. RF transmitter and receiver coils are required for MR imaging, while the transmit coils emits RF pulse with a typical peak power of few kilowatt in humans. The RF receive coil needs to be detected very small signals. Consequently, a special care has to be taken to avoid noise peak through the received coil, since MRI operates in a RF shielded environment. Both the PET subsystems and the MR subsystems need to be built in a way to avoid generating electromagnetic interference in the MR frequency band. During the development of a single integrated MR PET device, a major problem encountered was that the photodetector commonly used in PET, the PMTs, cannot be operated in the high magnetic fields required for MRI. In contrast, silicon has susceptibility of minus 4.2 into 10 to the power minus 6 and is therefore in- intrinsically MR compatible. Consequently, silicon-based photodetectors such as avalanche photodiodes or silicon photomultiplier tube (SiPMS) can also be manufactured to be MR compatible if sufficient care is taken to only employ material for encapsulations and the pins that have high magnetic susceptibility close to that of water. SiPMS in particular have an advantage compared to PMT, such as a higher intrinsic timing resolutions and considerably reduced dimensions. Similarly, all electronic components such as ICs, resistors, capacitors, connectors, etc., should be carefully selected with regard to the MR compatibility of the material used in these components. Precise attention is required concerning the connectors and pins of the components used in PET systems, as they are often ferromagnetic. However, a specialized supplier offer MR compatible alternatives. Close care is also required to the design of the printed circuit boards. The switching gradient fields may induce eddy current on large copper planes such as common ground and the power supply planes. Eddy currents may also be induced in loops within both the signal paths and the power supply path. In all cases, the induced voltages can cause additional noise on signal and power lines, leading to altered or falsely detected signal in the PET electronics. Most often, this reduces PET energy resolution and or cause and oblique or causes an altered PET signal count rate, both of which affect the quantifiability of the PET images. In order to improve the mutual electrical compatibility, at least the readout electronics and most often the whole PET detector modules are enclosed by an RF shield, which normally is integrated in the PET module housing. RF shields can be realized by depositing either structured or solid conductive layers which short circuits the E field component of the RF radiation. Care has to be taken since large conductive planes might cause eddy currents that can distort the gradient fields and therefore can cause artifacts in the MR image. The simplest RF shielding can be achieved by, by depositing a thin closed conductive layer on the PET module housing. However, in this case, fast varying gradient fields whose field vectors are parallel to the B0 field vectors will induce large eddy current on the PET module surface. Figure 10.1. Arranging interruptions in the conductive layers parallel to the B0 vector can efficiently reduce these ED currents. However, these interactions will act as a dipole antenna when integrated with a plane wave of wavelength gamma. The shielding effectiveness of a single slot length L is given approximately by SE is equal to 20 log lambda divided by L into decibel. RF radiation penetration through these slits can be avoided by connecting both conductive half surfaces with capacitors. The shield then acts as a low pass filter which blocks RF radiation close to the Larmor frequency but which only minimally affects the fields. Alternatively, carbon fiber reinforced plastic CFRP can be used since it effectively blocks RF radiation and also minimizes distortion of the gradient fields. In all cases, in all the cases discussed above, both the RF penetration from the MR transmit coil into the PET module and the pickup of electromagnetic radiation from the PET electronics inside the module by the sensitive MR receive coil is suppressed. It should be mentioned that the frequency of emissions RF emission by the by the MR transmit coils depends on the field strength and the image nuclei through the relation F0 is equal to gamma, gamma divided by 2 pi into B0, where gamma is the gyromagnetic ratio of the nuclei being imaged. The most important nucleus for MRI is proton. It has highest abundant in human tissue and also the highest gyromagnetic ratio, resulting in the highest MR signal of all MR visible nuclei. Depending on the field strength and the target nuclei, the Larmor frequencies can be very different. This has to be considered when designing the frequency selective RF shield for MR compatible modules. MR PET MR PET system architecture. In general, there are there are three general ways in which MR and PET can be incorporated in a combined device. The most straightforward approach is to combine PET scanner and the MR scanner sequentially. In this case, both scanners, this is the diagram, sequentially, here is the PET, here is the MR. In this case, both scanners are aligned along their system axis, and since their field of views do not overlap, simultaneous MR-PET imaging is not possible. However, this allows the optimization of both imaging modality to a maximum while mutual interference is kept to a minimum. Furthermore, if the distance between the both modalities is sufficiently large, it is also possible to use photomultiplier tube as a photodetectors, although additional shielding against the magnetic fringe field may be required. Most MRI scanners for humans have to be installed inside the Faraday cage to avoid the RF emission from the multiple and omnipresent electronic devices present in a normal environment to be picked up by the sensitive receiver coil of the MR device. The sequential MR PET configurations may be realized either by installing PET inside the Faraday cage in a separate room and combining the scanner through a subtle bed. In the case that the PET system is installed inside the Faraday cage, the PET device itself has to be carefully shielded to minimize the emission of RF noise. This allows alignment of both FOVs and simultaneous measurement, however, achieving sorry, another. This was the sequential. Another possible configuration, PET scanner is built as an insert for the MR scanner. This is the figure B. Here, MR is there and inside the PET module is there. This allows alignment of both fields, both FOVs, and simultaneous measurement. However, achieving MR compatibility is more difficult. The PET detectors and readout electronics is fully exposed to the static magnetic fields and switching gradient fields. Also, all components from the PET devices are very close to the MRI FOB, and even very small amount of incompatible material can cause significant artifacts. PET inserts for a standard MRI scanners will necessarily have a reduced patient port because the detectors and associated electronics can occupy additional space in the nearby confined gantry. समझ में आ रहा है मतलब बेसिकली यदि इनसाइड में होगा पेट तो जो क्वाइल्स जो होंगे बाकी जो मटेरियल जो एसेसरी चाहिए जब एमआर क्वाइल लगाते हैं ना तो उसके लिए स्पेस फिर कम तो बोर्ड का साइज जो है वो कम हो सकता है इसमें इसमें। और कुछ भी चेंजेस होगा वो वहां पे जाकर के मैक्सिमम आर्टिफैक्ट बहुत इजीली जनरेट होएगा। ऑल्दो मैन्युफैक्चरर ने जो भी बना रहे हैं उस पर तो काम कर ही रहे हैं लेकिन थोड़ा भी गड़बड़ होगा तो उसमें आर्टिफैक्ट दिखेगा। A wide A wide bore MRI scanner would allow for whole body PET inserts, but no combined wide bore MR PET has been built today. This is a potential this is potentially due to the cost associated with the wide bore magnet. इसलिए नहीं बना। Finally, the requirement of an RF shield for the PET modules makes them in general and opaque to the radiation from the integrated body coil, which is a large combined transmit and receive coil for a scout scan and body imaging applications that requires a large FOV. Thus, a dedicated joint transmit and receive coil that fits inside the PET insert is required. These coils must fulfill the spatial requirements that are explained in the next section. थर्ड ये हो सकता है थर्ड पॉसिबिलिटी है द पेट सबसिस्टम्स कैन ऑल्सो बी फुल्ली इंटीग्रेटेड इनटू द एमआर सिस्टम। यहाँ दिखेगा नहीं इसके अंदर डाल दिया राइट और ये पूरा का पूरा ऐसे क्लोज हो जाएगा। This allows the simultaneous acquisitions that both modalities for large FOVs and has the advantage that the body coil can also be used for MR imaging. The PET subsystem is embedded in the body coil and is therefore closer to the gradient coil, which can reach the higher temperatures. Consequently, a special care has to be taken to ensure good thermal isolations. All system designs all system design considerations mentioned for the insert solutions must also apply to the fully integrated MR devices. In addition to the latter two design approaches, In addition, the latter two design approaches, मतलब दो जो इंटीग्रेटेड जो होएगा, एक तो पूरा फुली इंटीग्रेटेड और एक इनसाइड, राइट, approaches require the use of silicon-based photo detector for the PET, SIPMT, basically avalanche photodiode. And as a consequence of their higher sensitivity to temperature variations, the liquid cooling of PET modules electronics is also characterized. A typical commercially available fully integrated human MR PET scanners and a smaller preclinical products are shown in figure 10.3. ये दो हैं, एक प्री क्लिनिकल और एक जो है ये वाला जो है तुम्हारा उसका सीमेंस का है, और ये जो कल हम लोग जो डिस्कस कर रहे थे मेडिसो वाला जो एनिमल स्कैनर जो है वो द प्री क्लिनिकल इन लाइन 1 टेस्ला एमआर पेट सिस्टम नैनो स्कैन with permanent magnet from the Medisho, and B integrated human 3 Tesla MR PET system from Siemens Healthcare GmbH. The PET detector rings is not visible, देखो, right? Not visible in the image, in the image of the Siemens systems. Image A is provided by the Medisho medical imaging systems, and B is provided by Siemens Healthcare G.